Active galaxies come in two types, Seyfert galaxies and quasars. The Seyfert galaxies are mostly spiral galaxies, with spectral line emissions from highly ionized gas. Quasars, on the other hand, have high redshifts, which indicate extreme distances from Earth. They also have luminosities up to 100,000 times the Milky Way's luminosity. Active galaxies have energetic non-stellar activity in their cores. These active cores have several important features, such as emission lines covering the entire EM spectrum, high luminosity, and rapid fluctuations in brightness. Now, what could be the source of these active cores? Rapid fluctuations in brightness indicate a small source object. Orbital periods of the stars near the core indicate a massive core. Therefore, large mass plus small size tends to indicate a supermassive black hole. The Seyfert galaxies are perhaps the largest group of AGNs. They tend to be early-type spiral galaxies with radio-quiet nuclei. They also have strong, high ionization emission lines. Their luminosity ranges from about 1/10 to 10 times that of the Milky Way. They are, in essence, low-luminosity, radio-quiet quasars. They also tend to be located relatively nearby to our own Milky Way galaxy. Quasars, on the other hand, are actually galaxies with an extremely luminous and energetic core. They are typically found at very large redshifts. Now, these redshifts shows that quasars are several hundred megaparsecs or more from Earth. To be seen at such large distances, quasars must be very luminous, typically about 1,000 times brighter than an ordinary galaxy. About 10% of all quasars are strong sources of radio emissions and are therefore called radio loud. The remaining 90% are radio quiet. Some of the energy emitted by quasars is synchrotron radiation, produced by high-speed particles traveling in a strong magnetic field. Blazars appear to be bright, star-like objects that can vary rapidly in luminosity. A high-energy jet of relativistic particles aimed directly at the observer probably accounts for their apparent energy. All blazars appear to be located in elliptical galaxies, and they emit polarized light with a non-thermal spectrum typical of synchrotron radiation. Blazars are probably double radio sources, but their orientation has the jets pointing straight at Earth. Their jets appear to emit material at superluminal speeds, up to 5 to 10 times the speed of light, simply because the relativistic jets are pointed directly at the observer's line of sight. Radio galaxies are elliptical galaxies located midway between the lobes of a double radio source. Relativistic particles are ejected from the nucleus of a radio galaxy along two oppositely directed beams. They exhibit narrow emission lines in their spectrum, and their luminosity is like that of the Seyfert galaxies, 1/10 to 10 times the luminosity of the Milky Way. By mapping the orbital periods of stars in galactic cores, it is possible to determine the mass of the core driving the displays of energy seen in AGN. These cores have shown masses in excess of 10 to the 6 solar masses. Coupled with a relatively small size, the only conclusion possible is that AGNs are supermassive black holes, with accretion disks of matter captured by the hole's gravity. The power source for these galaxies then becomes the gravitational energy released by this material as it falls toward the black hole. As material moves inward in the disk, it is compressed and heated to as much as 100,000 degrees Kelvin or greater, producing the incredible luminosity observed. It also emits far more X-ray and gamma-ray radiation than ordinary galaxies. Any variation in matter density within the disk will cause the disk luminosity to fluctuate, as has been observed. The conservation of angular momentum, though, prevents much of the matter from passing the black hole's event horizon. As a result, matter is expelled from the disk at right angles at extreme speeds in the form of relativistic jets. Magnetic forces play an important part with relativistic jets. The rotation of the accretion disk surrounding a supermassive black hole twists the disk magnetic field lines into a helix. The field then channels the flow of subatomic particles pouring out of the disk. Over a distance less than a light year, this channeling changes a broad flow into a pair of tightly focused jets, one on each side of the disk. These jets emit polarized, non-thermal radiation in the form of synchrotron radiation, produced by relativistic electrons traveling in a strong magnetic field, providing further evidence of the supermassive black hole engine driving the active galaxy. Quasars, blazars, and radio galaxies, once considered separate types of AGN, are now believed to represent only one type of active galactic nuclei. The determining feature is its angle of incidence to an observer. Face on with the approaching particle jet aimed at the observer, one would see a blazar, as we see in the diagram to the right. As the jet's angle moves away from the observer, the AGN begins to look like a radio-loud quasar. When viewed from the side, the torus and accretion disk block part of the particle jet. Combined with the jet pointing away from the observer, we now see the classical radio galaxy signature. In this animation of a supermassive black hole, the colors reflect the temperature of the gas dust around the supermassive black hole. Red-orange is hot, dark is cool. The animation starts with a face-on view of a gas disk, followed by an inclined view showing the cold, dusty molecular gas, the clumpy dark lanes obscuring the central source. The angle of incidence, I, affects the appearance of the nucleus as viewed by an observer. At I equals 0 and I equals 180, the relativistic jets are pointed straight at the observer, presenting the aspect of a blazar. The emissions from Seyfert galaxies tend to emit most strongly up to 100 kiloelectron volts. These emissions rapidly fade at energies higher than this. Emission from these galaxies are usually a smooth continuation of the X-ray emission. This generally indicates that the physical processes creating the gamma rays are thermal processes similar to those responsible for emission from galactic black hole sources. As a result, gamma ray studies of the high-energy spectrum and variability can give scientists important information about the physical environment in the AGN. Quasars tend to be observed at higher energies than Seyfert-type AGN, greater than 100 megaelectron volts. The highest energy observed has been in the tetraelectron volt region. Some of this energy is in the form of synchrotron radiation created by high-speed particles in a strong magnetic field. Spectroscopy is an important tool for analyzing the nature of AGNs. The visible light and infrared spectrum of this quasar, 3C273, is dominated by 4 bright emission lines of hydrogen. The redshift is Z equals 0.158, so the wavelength of each line is 15.8% greater than for a sample of hydrogen on Earth. Analysis of the spectra alone allows scientists to determine the distance of this quasar from Earth, 749 megaparsecs. This quasar also emits strongly over a wide range of wavelengths, from radio to X-rays. Quasar PKS 2000-030 has a redshift of Z equals 3.773. This redshift is so large that the Lyman spectral lines, Lyman alpha and Lyman beta of hydrogen, which are normally at ultraviolet wavelengths, have been shifted into the visible part of the spectrum. Its estimated co-moving distance is 6,947 megaparsecs. Spectroscopy is not the only tool used to study active galactic nuclei. This false color radio image of Cygnus A from the Very Large Array shows that most of the emission from this quasar comes from luminous radio lobes located on either side of the source galaxy. Red indicates the strongest radio emission, while blue indicates the faintest. Each lobe extends about 70 kiloparsecs from the galaxy. The inset picture, labeled B, is the galaxy at the heart of Cygnus A, and has a substantial redshift, so it must be extremely far from Earth, about 230 megaparsecs. To be so distant and yet be one of the brightest radio sources in the sky, Cygnus A must have an enormous energy output. The study of active galaxies and their nuclei has become an important field in astronomy, yielding new insights into galaxy evolution. This field will only become more exciting as new space observatories take to the sky.